Okay, so let's continue on. In this particular section, we are talking about rational exponents. Remember, rational is a fancy name for a fraction. So we are speaking about exponents in this section that happen to be in a fraction form. Here are our objectives. We're going to understand what the meaning of an exponent that looks like 1 over n means. What does it mean when it looks like m over n? And what if that m over n is negative? The negative one we've spoken about before. So let's start off with this. So notice first and foremost, n is a positive integer. What does integer mean? So sometimes it's better to explain what's not an integer. An integer is not a fraction, and it is not a decimal. So remember that. You are talking about n, which is in this case a number in the denominator, that is not a fraction or a decimal. Cool? All right. Now, notice how they rewrote this. 1 over n. So let me back up a second. We know what it means to have a to the power of 1, don't we? That's just a, isn't it? But now I have a denominator, and this denominator is telling me something. So check this out a moment. The 1 is clearly telling you it is a power. The denominator is actually letting you know what the root is. So, just like over in what they wrote, that is actually a to the first power. And the root we're talking about is the nth root. It could be a square root, a third root, a fourth root, whatever root. But understand, the numerator is always the power, the denominator is always the root. So, let's take a look in this particular case. Let's look at letter A. So remember, the numerator is the power, the denominator is the root. So if you rewrite it using a radical, that is technically the square root and 25 to the power of 1, right? Well, 25 to the power of 1 is 25, isn't it? And you know the square root of 5 as well as I do. 25 as well as I do, excuse me. Yeah, that's a 5. Good? Okay, so let's look at letter B. Again, the numerator is the power. The denominator is the root. So if you rewrite it using a radical, that 27 is to the power of 1, which is just 27. And they're asking me to find the cubed root of it. Yeah, 3. We've done that before, no problem. Okay, letter C. Again, the numerator is the power. The denominator is the root. So if we rewrite it using the radical, it's basically asking us to find the fifth root of x, isn't it? Which we clearly don't know because there's only one x there, isn't it? And since there's only one x, I can't take the fifth root of it, which is why the final answer is just the fifth root of x. Good? You with me so far? Okay. Let's check this out. Now, help me out. Answer a question for me. This 16, is the negative attached to it? Is the question. Does the negative and the 16, are they glued together? What do you say? I'm hoping you said no, for one simple fact. If the negative and the 16 were supposed to be glued together, then they should have been in parentheses like this. They should have been stuck together with parentheses and then the 1/2 on the outside. Are you with me? But since there are no parentheses in letter A, that means the only thing going under the square root is the 16. And the negative is just hanging out front, waiting for something to do. Let me write it a little bit differently. So maybe letter A could better be written as -1 times 16 to the 1/2 power. which means when you write it with the radical, it's -1 times the square root of 16. And you know what the square root of 16 is, right? That's 4, and the -1 is still out there, which is why your final answer will just simply be -4. Good? That's a little bit of a different way to look at letter A. Okay, let's take a look at letter B a second. Answer me something, please. What operation is between the 32 and that x to the 10th? Yeah, that's multiplication. So, do they have to stay together, or can I look at them separately? Right, we can look at them separately. So here's the thing. I can actually rewrite that as 32 to the power of 1/5 times x to the 10th, also to the power of 1/5. Not a problem. So, how do I write that 1/5 power? Yes, that means I have 32 to the power of 1, and it is the 5th root of it, isn't it? Okay, what about that x to the 10th? Same thing, that is the root of 5, and the power of 1 would just leave this as x to the 10th. Are you good? Okay, so they wrote it a little bit differently. They left it inside the radical, both inside the same radical, which is fine. Okay? And notice how they rewrote the 32. They rewrote 32 as 2 to the power of 5, didn't they? All right, well, let's take a look. If I have the 5th root of 2 to the 5th, what would I get? Right, I would just simply get 2, wouldn't I? And remember, the x to the 10th tells me there are how many x's here? Right, I'm going to write it up top here. So x to the 10th means I have got 10 x's. And for us visual people, it's not a bad idea to write these out till we get the hang of it a little bit better. And since I am talking about the 5th root, that means I need 5 equal pieces. Remember, 5 equal pieces. So, if I look at this, I have 1, 2, 3, 4, 5 equal pieces, each with 2 x's in them, which can be rewritten as x to the power of 2. Good? Okay, so we looked at letter B just a little bit differently, but we get the exact same answer. So it's up to you. Okay, you can keep it together in one root, or you can separate it out, your choice. So knowing that, look at letter C. Are there parentheses around the 7 and the x? Good, there is not. So this 1/5 power, what does it belong to? Does it belong to both the 7 and the x? Good, it does not. It belongs just to the x, which is why the 7 is on the outside of that radical, but still multiplied because there's multiplication in between them. So far, so good? Loving it. Okay, let's look at this next one. Now, notice I have that fraction exponent again, known as a rational exponent. M and N are still integers, and they're both positive in this case. Remember, the top number is the power. The bottom number is the root when this fraction is in the exponent position. So I'd like you to look at something. In this particular case, A is to the power of M, and then you have the N, or nth root. Agreed? That's actually the same as switching it around. I can take the nth root first and the power second. And sometimes it's actually easier to take the root first and the power second. Okay? So, let's take a look. Let's look at letter A. Now, I am going to do some work off to the side over here for letter A. I have 9 to the 3/2, right? That means I have 9 to the 3rd and then the square root of it. Well, help me out. 9 to the power of 3. Do you know that without a calculator? Yeah, no, most people don't. So here's the thing. Most of you will go on your calculators and you'll figure it out. And after all is said and done, that means you are taking the square root of 729. Answer me this. Without a calculator, do you know the square root of 729? Yeah, most people don't. Well, after you do the work on the calculator, you would simply get 27. Well, easy enough because I have a calculator to help me out. But you know, let's look at it a different way. As opposed to taking the power first, which is what we did, we took the power first, they're actually taking the square root first. So what's the square root of 9? Yeah, 3. The square root of 9 is 3. You know that without the calculator. And this 3 is still to the power of 3 because you still have to deal with that third power that we haven't done yet. And I still get 27. I get the exact same answer. But one way, like how we did it over here, this requires me to get on that calculator and hopefully I'm finger punching correctly. The way they took care of letter A, I actually really didn't need to use the calculator. I just needed to know the square root of 9, which was 3, and then know what 3 to the power of 3 was, and we're good to go. Okay, so far so good on that. Does that make sense? So, it's easier to take the root first, like they did in letter A, and the power last. Okay, before we start letter B, question. Is the negative and the 256, are they stuck together? Good, they're not. Why not? Right, there are no parentheses keeping that negative with the 256. That's not what we have, which means when we look at this, we actually have the 256 under the fourth root with the negative on the outside. Remember, the top number is the power, the bottom number is the root. And as we saw in letter A, it's easier to do the root first. So you've got to know what the fourth root of 256 is. Well, at least it's easier than trying to figure out 256 to the power of 3 first. That would just be an awful number. Not an awful number, but an extremely large number. Okay, I'll wait till you get on the calculators. Fourth root of 256 is? Good, 4. Notice the 4 is in the parentheses with the negative on the outside, right? Because the negative did not belong on the inside. And now you need to know 4 to the power of 3, which is why the answer is negative 64. So far, so good? Y'all with me? Okay, so let's look at letter C. Notice that parenthesis has the 2x plus 1 inside of it. And according to this exponent, we have the power of 2, and we have the root of 7, which is why they've written it this way. How many parentheses are underneath? Yeah, only 2. And what root am I taking? Yeah, 7. Do I have 7 of a kind? No, which is why the final answer on letter C stays this way. Y'all with me? Okay. Now, notice this particular definition. We know the m over n already. This is nothing new. What we need to remember is what the negative on an exponent means. Yeah, the negative on the exponent tells you that this a is in the wrong spot. This negative tells me to move the a. And notice the definition. The a went from the top to the bottom. The exponent is now positive because we moved it. And the m over n, we already know how to deal with it. Why? Because look at these last 3 problems. We dealt with the exponents that were fractions already. No big deal. Okay, let's look at some examples. Now, there are a couple of different ways that you can actually handle this. You can deal with the negative first, or you can deal with the negative last. Some people rather deal with the negative first, going, okay, 64 doesn't belong on the top, it belongs on the bottom. And when we put it on the bottom, the exponent of 2/3 is now positive. Okay, remember, this 2 is the power, this 3 is the root. And as we saw on a previous slide, it's easier to take the root first. Because most of us, as long as we've been doing our homework on these last couple of sections, know the cubed root of 64. What is it? Yeah, it's 4. See? 4 to the third. Which means the cubed root of 64 is 4. And then all I got to do is figure out 4 to the second, which is 1/16. Cool? Good. Loving it. You getting the hang of this? Good. These two examples, A and B, are exactly like what we did on the previous slide. The only difference is I now have an exponent that's negative, which is telling me my answer doesn't belong, in this case, in the numerator. It belongs in the denominator. Okay, look at letter B. In letter B, is the negative on the outside? Is it part of the 16 right now? Good, it's not. Which is why it's sitting out front here waiting for you to do something with it. But notice the negative power told me that this 16 belonged on the bottom, and then the 5/4 became positive as soon as you moved it. Now, what's easier to take first, the power or the root? Good, the root, which is why they've written it this way. They skipped a step, so for those of you who do not like step skipping, let me get a middle step in here for you that you would like to see to help yourselves out. We have the 1/, yes, the negative is on the outside, and we said it's easier to take the root first. So we got the 4th root of 16, and then the power of 5. And 16 can be rewritten as 2 to the power of 4. Okay, that better for those of you who said I don't like the step skipping? Good. Well, I'm taking the 4th root of 2 to the power of 4. What do I get? Correct, just 2. And now I've got to figure out 2 to the power of 5. So you can do 2 times itself 5 times, or some of you may put it into a calculator. Regardless, you're going to get a negative 1/32. Cool? Loving it. Okay. Getting the hang of this? This is a combination of taking powers and roots. It's their way of getting you to do 2 problems in one. Now, I am going to go over, with these next couple of slides, the rules of exponents, which you have done before. So this is really nothing new. The only thing you need to realize is that these exponents that we're going to be working with are now fractions. But that's okay. We know how to deal with fractions. So remember, when you multiply the 2 of the bases that are exactly the same, you get to add exponents. If I have parentheses in between numbers, what does that usually tell me to do? Yes, it tells me to multiply, which is why I'm multiplying these 2 exponents together. You can only multiply an exponent to another exponent. Okay, when I have a number outside parentheses, I still get to multiply, don't I? Now, mind you, the power on the A is 1, the power on the B is 1. So 1 times n is just, correct, n, which is why I have a to the n and b to the n. And the same thing with this fraction. The power on the a is 1, the power on the c is 1, and when you multiply those together, I get a to the n over c to the n. Remember, I get to multiply exponents to exponents. Good? Okay, so let's see what you remember about when you divide the same bases. These bases are exactly the same, which means I subtract. And I'm going to take the numerator minus the denominator. Cool?
Okay, notice the restriction. The restriction says, hey, your base can't be equal to 0. Makes sense, right? Because if a was 0, I'd blow up my fraction. That would be undefined, wouldn't it? Cool. Let's look at something else. Remember, a to the power of 0 is 1. And those negative exponents, which we already dealt with, tell you to move these variables. So let's take a look. The key to combining any of these is making certain that your bases are exactly the same. And in this case, they're exactly the same, which means since I am multiplying and my two bases are exactly the same, what do we get to do between the exponents? Good. Hopefully you remembered the last slide, and that means you get to add the exponents. But you're adding fractions, aren't you? And in order to add fractions, what do you need? Yeah, you need a common denominator. So remember, that means you need to make these denominators look the same. And what's the common denominator with a 3 and a 4? Good. I heard some of you. 12. So the 3 needs to get multiplied by 4, and so does its numerator. 4 needs to get multiplied by 3, and so does its numerator, which is why we end up with 4 over 12 plus 3 over 12, which 7 over 12. Now, they may ask us to leave it as an exponent, or they may ask you to write it using a radical. If they ask you to use a radical, that means you have x underneath definitely. What's the 7? That's right, it's the power. What's the 12? That's right, it's the root. So they may ask you to write it using a radical. So just watch the directions. They will tell you if they want it left as a rational exponent or if they want it written as a radical expression. Okay, and this I should spell out because the abbreviation could be the same. So just watch their directions. Okay, so let's take a look at letter B. In letter B, I'm doing what operation? Right, we're dividing. And according to that last slide, when you divide the exact same bases, what do you get to do to the exponents? Correct, you get to subtract. And notice the numerator minus the denominator. And these are fractions, aren't they? Well, gratefully, these fractions have the same denominator, don't they? Good, so I don't have to worry about that. So I end up with a negative 10 over 5 when I do the subtraction, yes? Okay, remember though, what do you always do with a fraction whether they tell you to or not? Good, you reduce it, which is why the negative 10 over 5 reduces to a negative 2. But that negative means, and I'm going to back up a slide, that negative means that the 9 belongs on the bottom, doesn't it? Which is why we end up with 1 over 81. Cool? Okay. Now, letter C. Letter C can be handled a couple of different ways. So let me take a look at letter C with you. Notice this first y has a negative power, doesn't it? And the second y does not. So one way to handle this is to actually take this first y and put it on the bottom. But notice the power goes positive. Good. And we still have the y to the power of 6 over 10. Well, it looks like I'm just multiplying a couple of fractions, which means I would end up with y to the 6/10 over y to the 3/10. And when you divide, as we saw in letter B, you get to subtract those exponents, don't you? The numerator minus the denominator, which will give me simply, good, y to the power of 3/10. Now, letter C, they handle a little bit differently. They're like, well, great, since the bases are the same, I simply, and since there's multiplication, I simply get to add the exponents, which still gives me y to the 3/10. So, depending upon the problem, sometimes it's quicker just to do as they did in letter C, or sometimes the way we approached letter C might be more appealing to some people because they don't like the negative exponent at all. So your choice. All right, now let's look at this. They want us to simplify. Now help me out on letter A. How many y's do I have? Yeah, I've got 5 y's. And this 10th root means I need 10 of a kind, right? Well, if I only have 5 y's, I don't have 10 of a kind, so I can't really take anything out, can I? But we can still simplify by shifting this into reverse and going backwards. Remember, we have a power and we have a root. So we can rewrite this as a rational exponent. Five over 10. The 5 is the power, the 10 is the root. And I can simplify 5 over 10, can't I? Good, which gives you 1/2. And if they want me to leave it with a rational exponent, I'll leave it that way. But if they want me to rewrite it with a radical, this is what it's going to look like. Remember, the square root is there. Good? Okay. Now, let's look at letter B. We're trying to find the 4th root of 9. Well, we know that there's not a 4th root of 9 without going to the calculator. There's a square root of 9, but not a 4th root of 9, right? Okay. But let's think about this. Humor me a second. Can I rewrite the 9? Because 9 is a perfect square, isn't it? So couldn't I rewrite 9 as 3 to the power of 2? And I'm going to look at it a little bit differently than they are, but that's okay. We get the same answer. So here's my letter B over here. I've got the 4th root then of 3 to the 2nd, don't I? And couldn't I rewrite this as a rational exponent? The 2 over the 4, which would give me 3 to the 1/2 power, wouldn't it? They rewrote it with the radical first, switched to an exponent, and then they realized, hey, 9 is 3 to the 2nd. And then they multiplied their exponents together, and then they finally got what we got, 3 to the 1/2. So it's your choice to rewrite the radical first or to rewrite the 9 first like we did. Now again, if they want it written with an exponent, you would leave it as 3 to the 1/2 power. If they want a radical, then they will tell you, which means you're dealing with the square root of 3. Cool? Okay, let's check it out. Oh, they want us to simplify these radicals. Now help me out in letter A. This is a square root, isn't it? And can we take a square root times a cubed root? I know some of you aren't sure about that. Well, let me sidetrack you a second. If I take the square root of 2 and multiply it by the cubed root of 2, is the square root of 2 the same exact value as the cubed root of 2? And if you're not sure, go to your calculator. This is about 1.4. This is about 1.7, I believe. And I could be wrong on that. And some of you, I think, are going to double check me. You're like, I don't believe you, which is totally fine. As a matter of fact, I'm going to check myself, and that's actually 1.2. They're not the same. So I can't multiply these two radicals because they're not the same. But if I rewrote them, y, the square root of y, can be rewritten as, remember that y is a power of 1. That's y to the power of 1 over root of 2. And the cubed root of y, and the y as the power of 1, can be written as, power of 1 over root of 3. And now I've got a problem, like I did a couple of slides ago. Since the bases are exactly the same, what do I get to do to the exponents since I am multiplying these two? Good, you get to add them. And to add fractions, what do you need? Good, a common denominator, which in this case would be 6. And I'm going to put a middle step in here because I know how most of us like a middle step. And here's my middle step. 1/2 becomes 3 over 6, doesn't it? Because you multiply both of these by 3. The 1/3 is 2 over 6, isn't it? Because you multiply both of these by 2, don't you? And that's how we end up with the 5 over 6. Cool? Okay. Let's look at letter B. Letter B is kind of interesting to look at, but we're going to tackle it the same way. Even though the 5 and the 2 don't have the same base or are not the same base, I can actually still deal with this problem. I'm going to do the same thing. I'm going to rewrite that 5 is to the 1/2 and 2 is to the 1/3 power. Now, if these bases were the same, and since we were multiplying, we would try to add the exponents, wouldn't we? Okay. And if we added the exponents, that means we would need to have the same denominator like we did over here, right? So we're going to try this and see if that works. We're going to get the same denominators. So I can change both of them into a denominator of 6, which means the 1/2 changes to a 3 over 6 and the 1/3 changes to a 2 over 6. Agreed? Okay. Now, here's what I'd like you to notice. They both have a denominator of 6, which means they both are the root of 6. 5 to the 3 over 6 is basically the 6th root of 5 to the power of 3, isn't it? And 2 to the 2/6 is the 6th root of 2 squared, isn't it? So, they're doing it a little bit differently, but that's okay, because notice I have the 6th root of 5 to the 3rd, now times the 6th root of 2 squared, right? Since the roots are the same, I can now multiply 5 to the 3rd times 2 squared. So this is the only step that's different than from what we did. But we ended up right here at the same step. And I end up with the 6th root of 500. And now you're like, oh my gosh, I have to simplify that. That's true. You can try to simplify it, which means you're going to need how many of a kind? Yeah, you're going to need 6 of a kind. But before you try to figure that out, go back here. 500 was made up of 3 5s and 2 2s. Do you have 6 of a kind? Nope, which means that would be my final answer. Cool?